What are promises? Promises are very common in our day-to-day communication. For examples like, I promise you that I will walk the dog. I'll lock the door when I leave. I promise not to lock the door when I leave. Like, I know that your mom's coming in town, she doesn't have a key and she has to be able to get in. It's going to cause a problem or whatever. We'll definitely wash our hands before touching the food, or a simple promise like, I promise to stand on my head during this presentation. My name is Aaron Blythe, and I'm a software architect. My talk is entitled Promises, Promises, and my talk is about promise theory. Promise theory was proposed in 2004, so it's been around for a decade now. As of February 2014, you can go out and buy it on Amazon. Promise theory was written by two wicked smart PhDs, Mark Burgess of Oslo University College in Norway, and Jan Bergstra at the University of Amsterdam. In 2004, Burgess was contacted by Jan Bergstra at the University of Amsterdam looking for scientific backing for a proposed one-year master's degree course at the university in system administration. In spite of very different backgrounds, they shared a likeness of mind in their attitudes to science and research. This resulted in them becoming friends and going on to discuss and hone several parts of promise theory together on mutual visits between Norway and the Netherlands. Oops. While researching this presentation, I noticed there was no mention of promise theory on Jan's Wikipedia page, so I fixed that. So it's there now. Mark Burgess is incredibly accomplished. He's a PhD in theoretical physics. He's the creator of CF Engine. He patented an algorithm to improve Google's PageRank. He's also made major contributions to configuration management. One of those being convergence of state, and the other one being promise theory that we're going to talk about today. In 1994, Mark registered CF Engine with the Free Software Foundation under the GNU public license. CF Engine was created nearly 2 decades ago when Mark was well under the age of 30. CF Engine 2 brought us the idea of convergence to a desired state and self-healing, or computer immunology is what we refer to it as. Luke Cannies was a power user of CF Engine 2, however, he wanted more, so he created Puppet. Adam Jacob was a power user of Puppet, who wanted more than the default non-deterministic graph-based ordering that Puppet has to offer. I have to admit that I've only used Chef, although I've used it extensively for the last 3 years, and I personally am still taken by its mix of the clean DSL and pure Ruby. Promise theory was created around 2004 and only truly brought to light in CF Engine 3, although it has influenced all 3 of these tools. I've had the privilege to see Adam Jacobs speak in person 4 times now and many other times online, and he pretty often gives major props to Mark Burgess. It was actually a discussion I had with Adam Jacob where he introduced me to this theory. So what is promise theory? Directly from Mark's blog, like any scientific method, promise theory is not a solution to anything. It's a language to describe and discuss cooperative behavior. Mark gave a talk on the future of configuration management less than a month ago. In this talk, he talked about the idea of statelessness, that all states converge to a promise. What we want to think about in configuration management is this chemistry of these atomic elements, those atomic elements being files and processes, database tables, network interfaces, and services. Promise theory is a book that's 215 pages. It reads like a college text. I've read through it twice, and it reminds me of doing proofs in like high school geometry, or doing theoretical and applied mechanics when I was in college, which is actually something that I quite enjoy. While I don't have time to go into depth on the entire book, I do want to spend some time on the tenets of promise theory before we jump into examples. The first one is that agents are autonomous. They can only make promises about their own behavior. No other agent can impose a promise upon them. A promise is a signal, as perceived by the observer, or what we're going to call the promisee. It involves passing information to other agents or to many agents. Promises themselves may or may not be kept. The assessment of whether a promise has been kept or not may be made independently by any agent that's within its scope. The interpretation of a promise may be made independently by any agent that's within its scope. Promises imply that there's a transfer of information from the agent making the promise to those that learn of its content. And the internal workings of other agents are assumed to be unknown. So knowledge of agents only comes from the promises they make and the promises that they seem to keep. So internally, an intention is the subject of a possible behavior, such as later, I intend to stand on my head. As this is brought more publicly to the external world, it can be conveyed as either a promise, an imposition, or an obligation. Once an agent has published their intentions to other agents, it moves on to either cooperation or compliance with those other agents. Finally, there's an assessment that's made by the agents that are within the scope. In philosophy, the concept of promise has been discussed for the most part in the connection of morality. It's simply assumed that a promise just implies an obligation to keep that promise, referred to as the promissory obligation. In promise theory, we're given the opportunity to have just the promise, leaving out the subject of morality or obligation. An obligation carries this weight of potential consequences of not acting, so promises are fairly subjective to begin with. Why would we want to compound that with all these other layers of subjectivity? Further, obligations limit us to just the discussion of promises that refer to a future action. So Burgess uses promises to measure voluntary cooperation, to get around all the fundamental problems with the logics of obligation and determining what the system behavior. So voluntary cooperation is a way of simplifying constraints and avoiding the many worlds problem. There's a large benefit to this pragmatic approach. It makes the mathematics of it quite a bit simpler for the engineering mind that's trying to set up the systems. In February 2013, John Willis gave an excellent talk entitled Promise Theory for Dummies. What I took from this talk was that obligations assume facts. In engineering, we know that making assumptions leads to a lot of problems. So obligations oversimplify things. Like if we make the statement that DNS must work, whereas promises, they imply a contingency. What happens when DNS doesn't work? Have we built that into the system? I highly recommend John Willis's talk as he walks through the history of management, noting that many of the big names in scientific management in the last century, like Deming, Shewhart, Goldratt, all started and were classically trained as physicists, just like Mark. So after the event has occurred, then an assessment is made by an agent that's involved in the promise. So taking a couple examples directly from the text of promise theory, there's a promise like feed the cat. That's represented by a speech act. The scope is those who heard that, and the assessment is either it did or did not get fed. So if we move this to code, the promise is that this variable equals this value. The representation is source code. The scope is the readers of that code, and the assessment is the syntax is okay and the value's in range. If we move that to object code, the scope is the execution engine, and the assessment is that that's okay to execute, so we go forward, or it's not okay to execute, so we throw out an exception. The notation of a simple promise is fairly simple. As a promiser, one agent promises something to many promisees, one or many promisees. The body of the promise is written above that arrow. For an imposition, an imposer, one of the agents imposes something on one to many of the imposees. The imposition is meant to look like a fist. That's why we have the square there, whereas a promise just has the arrow of pushing the information. So if we take a simple example directly from the text, what we have here is you can see how it integrates into math with the set notation. So a parent promises its child that one of the people that are trusted will pick them up from school. So let's make this more real. So if I promise to my neighbor that I'm going to bring over some beer, that would be shown like this. Aaron promises to bring beer to neighbor, for poker night or whatever. Now, if my neighbor in turn promises to drink some of that beer, that would be shown like this. I want you to notice the polarity. I now have a negative sign on my promise. to show that the neighbor is accepting this offering of spirits. This is a good thing because we now have cooperation and beer. So here's another promise. Aaron promises the audience that he will stand on his head. I actually made this promise a couple weeks ago. The exact text of what I said was, I promise to stand on my head during this presentation. But each of you out there are autonomous agents. So if we scope this differently, I made this promise to each of you. So I can further model this as making this promise to each of you. This is a reminder slide that I'm supposed to stand on my head. Tuck in here. Oh, did I hit it? Did I hit the middle button? Do you guys know how to get out of that? They told us the middle buttons messes it up. I didn't hold it. I got time. I'm going to try to do it again. What's that? Okay, I will. What's that? Okay. That's why it was in my hand, and that's why I messed it up. Sorry about that. So each of you in the audience is an autonomous agent that has the ability to assess what just happened. Was the promise kept? Me as the promiser, there's many components to the promise. One of them is the promise. What outcome did I intend? Another one's the algorithm, is like, how is the promise kept? Another one is my motive, like why did I make that promise in the first place? Another one is context, like where and when the promise was made. I made it on a message board. You as the promisee, there's many components to yours. The outcome, what was measured during your assessment, so you visually saw me stand on my head. The context, like where was the sample taken? The algorithm, the motive, and the expectation. So what were you expecting to find when you were assessing that promise? Maybe if you saw the post, you could construe what I did as an imposition. You are an independent agent, each of you, and that would be fine. Remember, an imposition is a message intended to induce voluntary cooperation to another agent. Impositions are not promises because they cannot be kept by the agent who makes them. So examples include like hints and suggestions, requests and proposals, requirements and specifications. That's an interesting one because that's what we write quite a bit in software, is requirements and specifications. Commands and demands, also an interesting one because the way we often think of setting up a machine is running a bunch of commands. Had I instead said, if you come to my talk, you will see me stand on my head, that would have more likely been an imposition. Maybe what I just did could be construed as an obligation. Obligations are stronger forms of impositions as they imply some form of penalty for non-compliance. Had I instead said that if you don't come to my talk, I'll beat you up, that may be like an obligation. You may feel obliged to show up because you don't want to get beat up, but that's just a difference there. Okay, so when we're talking about promises, we have to take into account that there's liars in the world. A deception happens when there's two intentions. Had I posted that I promised to stand on my head and you read that, being the promisee, however, secretly, internally, I never intended to do so, that would have been a deception. So since there are liars in the world, we also have to have the idea of trust and expectations. I trust my computer to give me the right answer. On the left, we see the notation for trust, which is equivalent to that notation on the right, where a promise is wrapped in an expectation. So my initial examples were of humans making promises. To understand promise theory, we're going to need to think of inanimate objects as making promises. So something like, I am a meat knife, and I promise to cut more efficiently through meat. Or I am a logic gate, and I promise to transform a true signal to a false signal, and a false signal to a true signal. Or I'm a highly available server, and I promise use service within like 6 nines of availability. So now that we have the base fundamentals, let's take this to an example in DevOps. Here we see a simple system that's really common. A client makes a call through a dispatcher, often referred to around here as a load balancer or a proxy, to a group of servers. On the left is a simple flow of information here. And on the right, here's the hardware that we need to accomplish this. This is very common. You may have drawn this on a whiteboard somewhere around campus in the last month. I know that I have. So in that talk I was talking about earlier, in Burgess's recent talk, The Future of Configuration Management, he said, if you do the whole flow charting thing, first do this, then do this, then do this, all you'll ever know is what you ended up with. You don't know if you can ever do it again. And the system doesn't have a recipe for healing itself. So if you've documented the promises that make up that flow chart, then you know every single thing that can fail. You've got a list of possible failures. So here we have 3 flow charts for possible architectures of this client to server interaction. If we stop here, we just have the diagram. So if we take this a step further and apply promise theory, now work with me here because I'm actually going to walk through just this first one. I'm not going to put you through walking through all 3, and I'm going to do so quickly. But the client imposes a request. Notice the fist. The dispatcher promises to accept request. Notice the negative polarity. The dispatcher promises to select a server from the pool if it knows the server queue length. The servers promise to accept requests from the dispatcher. Servers promise to report their load to or queue lengths. The servers promise to reply to request with service response to the dispatcher. Dispatcher promises to accept server responses and queue info. Dispatch promises to forward replies back to the client. And finally, the server promises to deliver the same service content to all of its clients. I'll save you walking through each example, like I said. So here the change that was made was that the servers deliver the responses directly back to the client instead of going back through the dispatcher. And finally, we remove the dispatcher altogether. So let's put these side by side. Promise theory can be used to compare these 2 designs. As we move to the right, we're increasing in complexity. But eventually we reach a point where we want to strengthen the system. So we add redundancy on the client cluster. You can see that the number of lines, remember each line represents a promise, has gone up. Our system has more points for failure and thus is more fragile. But wait, our original intention was to make a stronger system, but we just made it more fragile. These are the type of things that are made a lot more apparent by applying promise theory. So that's one of the major benefits. All of Chapter 10 is devoted to the idea of trust. One way that we can mathematically evaluate trust is to apply probability theory. Remember that probability theory is built on the assumption that past evidence can predict the future. The big question you have when you're doing probability theory is like, how do we initialize the system? If we have a really trusting system, we're going to initialize it with the value of 1 and start applying probability theory there. If we have a neutral system, we'd initialize it with half, and then if we have an untrusting system, we'd give it a value of 0 to seed it. One's own direct experience of a service or a promise usually is the first thing that we use as a basis for a trusting agent in a network. However, an optimistic agent might choose not to allow the past to rule the future, believing that agents can change their behavior. Like in the world, this just means like, oh, that server was having a bad day, so we're not going to necessarily base all of it on that. Another model is advice. An agent might feel that it's not the best judge and seek the advice of a reputable, trustworthy agent. That it's kind of the model of like, let's see what X thinks. So if in the real world, like you're gonna have someone work on your house or whatever, then you might go to Angie's List and see the comments back from other people. Another model is reputation. Again, you might go to Angie's List, and it's not necessarily the comments that you're looking at, but it's the overall like numbering system of, is this the best service that I can get? Some agents you may model as that if an agent fails even once to fulfill a promise, then it's completely untrustworthy. This is a really extreme policy, and it seems kind of excessive, since there might be reasons beyond the control of that other agent to prevent it from delivering on its promise. But it depends on what the system is that you're building. Like maybe that's the exact right thing to do, is say, once something fails, then we don't use it anymore. This is probably the obligatory mention of Netflix or whatever as they're spinning up new things in their cloud. So why does any of this matter? The number of servers that we're using to deliver technology is growing exponentially. It's doubling more often than every 2 years. The existing models of command and control are not going to scale as we continue to go up this curve. Promise theory helps us ensure that the system level certainty of that entire system by focusing on that component level uncertainty. So if we know all the promises that are made from each individual piece along the way, we've modeled that, and each of those are individually resilient, then the whole system ends up being resilient. So in addition to system architecture that we build, those diagrams, the flow charts and stuff, we should also be documenting risk assessments. We should have disaster recovery plans. We should have failover plans. We can build all of these by applying promise theory. So what promise theory is going to give us is this common language of promises that not only helps us design our systems internally, but also helps us to continue to build in resiliency as we go. I've been through some of these exercises recently, and because we didn't keep track of all of our promises throughout, you get in a room with people and talk about disaster recovery, and everyone just tries to remember everything. It'd be really nice to pull up, here are the things that we know that can fail. Do we have a contingency for this? If we don't, we schedule that work and appropriately, but building that list has been very hard on us at this point. So we want to build in that resiliency while we continue to build in the features that we can get out to our clients. This is directly from Mark Burgess's blog. It's about DevOps. Now remember that Mark was in the configuration management game years before Flickr brought us the 10 deploys a day presentation. So I'm going to go ahead and read this. I know this is against the rules of just reading the slide, but it's really good. There's a basic conflict of interest between the roles of the developer and the operations engineer that are not typical of the supply chains of other industries. Web developers are motivated to push out new goodness as fast as possible. Infrastructure engineers often have little incentive to change anything. They are used to being ignored until something goes wrong, whereupon they are the first line for blame for the fault. Deploying something without due diligence would only land them in trouble. To developers during the web boom, operational resistance was the problem. To operations, developmental change was the problem. There was an impedance mismatch in the cooperation circuit that needed fixing. Enter DevOps. I really like that quote. Sorry, I just had to read the slide. Going beyond DevOps to Lean, when we're applying Lean, what we're looking for is flow, or in the case of this picture, the lack thereof. Requesting an ACL is a very common task in DevOps. For those who don't know what an ACL is, it's an access control list. These are commonly used in security and networking to represent that X can connect and talk to Y over here. But what are the expectations on such a request? If a promise is published that the work will be completed in X amount of time, then expectations can be built upon that promise, like when to request. If it takes me 5 days to get an ACL, then I request it at least 7 days before I need it. From this simple promise, we can create the flow. If no promise is published, or if the promises are not kept, then the system produces what we refer to in Lean as waste. The requester may not know when the appropriate time to make the request for the ACL is. Then asking late causes them to have to escalate, and then that causes waste. Or if the requester is not given expectations or visibility then they also have to continually keep asking for status on this. That creates waste on both sides of the requester and the person doing the work, especially when it's something that relatively is 5 minutes of work. Now I want to talk about convergence versus congruence. This goes a little bit beyond promise theory, but the convergence of state. Convergence focuses on the outcome and then converging to that final state. So congruence is like, that's convergence, okay. Congruence is like starting from a blank slate and then changing the system in small increments until it gets to some state. So kind of massaging it till it gets there. Unfortunately, that state is often not clearly defined and the changes are not clearly documented. Deming refers to this as tampering with the system. This is actually how by eliminating tampering, is how they got manufacturing to get to such a quality state. When we use a GPS, we simply put in the destination. Many GPSs actually work backwards from this goal to where you are now. There are many ways to get to that single goal. This is the model that Mark uses to explain convergence. So like when we're running configuration management on a node, when we're running Chef Client or something like that, we can continue to run Chef Client over and over and over until that node gets to the goal state. The discussion out in the DevOps community around this is whether order matters. Of course it does. The discussion on order mattering is public, and you can read about it in Steve Trogut's paper or Mark's response. Both of them are awesome. I could do an entire talk on this topic. So where do we go from here? We need to have more discussions on this topic. I would love to have those discussions with all of you. I'm the organizer of the DevOps Kansas City meetup. I'd love to have more talks on configuration management building blocks and the theory and the application of such theories. We also need more examples out there of promise theory applied out on the web. It was very hard for me in making this presentation to find really good examples. I had to make things up like taking beer to my neighbor and standing on my head. And also, as Julia Grace eloquently put it yesterday, we need to lower the barrier of entry so it's not just nerds like me that like to read a textbook on the weekend and do a presentation about it. They can understand and apply these theories. So my question to you is like, how do we change our thinking? So that's my talk. Does anybody have any thoughts and or questions?
I'm just curious about the polarity diagrams that you used.
Yeah.
In the first one with the bringing beer to the neighbor's house,
Mm-hmm.
you have the order of the parties the same. You have you on the left and the neighbor on the right.
Yes.
In the second one with the client and the server, or the client and the dispatcher partnering, you changed it so that the dispatcher was on the one for the response, but you also added the negatives. Before that, I think it was on the eight. But you kept the negative polarity, and I was confused as to what was going on.
That's a really good question. This is just a screenshot from the text, and I struggled with that exact same thing. I've changed the thing back and forth 3 times before I finalized on what I had there, and I had to go back into the text. So there are a few things that I've noticed, and I'm actually probably going to send to the authors about. They've clearly stated because that they don't want like grammar fixes or whatever, but there's a couple of things that are really kind of off here. If you look at this one here where client and dispatcher are switched versus this one here, No, it's a different promise. I think you're probably right. I think I probably didn't land on the wrong one. But there are a couple of other things that I have for errata for them. So that one was me, not them.
Have you used charts like this on any of the projects that you've worked on? Like, are there examples that we could look at in Cerner?
The question was, are there examples of the application of this in Cerner yet? I am not aware of any. I only finished this presentation about 5 minutes ago. No, but this is something, part of the driver for this was that I want to start applying this in our thinking. So going forward, I do plan on our team to start using this methodology and going through the exercise of doing that, but I'm not aware of any applications of this yet. Any other thoughts? It's pretty heavy to present a textbook at a conference. The question was, do you think that this is one of the first steps towards designing like operations science? I do. I think that you were referring to last year, someone from Chef did the keynote here, and he referred to like there's not as much science in this. Mark is one of the few people who's written a textbook where they've really tried to deeply go into applying algebra, set notation, and theory to this. There are a couple more, but I do think this is one of the main building blocks that we need to start entering this thinking. Now, I don't know that it's in our best interest for us to all become like uber math nerds over this. But there have been times when we've applied different like Bayesian algorithms and like a lot of cool math, like a lot of the stuff they're doing in Cerner Math. So I think that yes, this is one of the cornerstone building blocks that we need to start thinking this way. So we need to take the text of this and really break it down to processes that we can consume very easily, both in development and operations. And as a language to speak between development and operations, to have these conversations earlier instead of later on after the system has already been set up. Or as we move to multi-data center type of deployments and everything, this will make that conversation go a lot smoother.